starting off, the information for Big Idea 1 is going to come from chapters 2, a very little bit from chapter 3 and chapter 7. So this is going from the structure of the atom, waves, all that good stuff, and then going to end at compounds, bonding, or at least the basics of bonding, naming, and so forth. Following along in the slides, or if you have your review books, you can feel free to make notes, highlight, those types of things. If you need highlighters, I have a big box of them over here. Merry Christmas if you need one. So, let's get started. So, giving people a chance. All right. Now, to give you a little bit of background on the atom, chemistry, and so forth. The beginning, or the first big idea in the first place, the goal was to study the structure of the atom and start to see how that's going to play a role in bonding and all the other things that come with it. So, first off, we start off with our good buddy Democritus. We talked about him briefly. The basic idea that he said we have to get to a point where we can't break anything down any further. He called that thing atomos. We're good to go. He had no no evidence. Therefore, 2,000 years went by before anybody thought about what he said. Robert Boyle comes in with the same idea. Says we have these things again. Still have no idea what they're called, but he started to get together some of the properties. Most of the early chemists, you'll notice they worked with gases. Why gases? Well, they surround you. Kind of easy. So, moving on from there, that takes us into a couple of our early laws. These are three main ones that you want to make sure you have note of, circle, highlight. Math-wise, they may come back, especially this one. But law of conservation of mass, we've dealt with before. Can't end with something I didn't start with, or vice versa. That being the case, we always have to make sure, unless it's a nuclear reaction, we have the same amount we began with at the end. Law of definite proportions, basically every molecule or formula unit of sodium chloride will have the same amounts or the same percentage composition by mass. So I should not get a sodium chloride that has 2 sodium with 1 chloride. That doesn't exist. It can't exist. Okay? Next one, law of multiple proportions. Dealing mainly with, our covalent compounds, because we can have multiple compounds that have the same 2 elements, but because of the bond structure, they can be completely different properties. It's basically saying, if I have nitrogen dioxide, I'm going to end up where I can also work it down to a straightforward ratio. This was our good friend Dalton, who also gave us what? What did Dalton give us? No, he didn't give us the structure of the atom. No. Ooh. I'm scared. Shh. Dalton gave us, I heard somebody say, Electron. His atomic model was describing what? We're overthinking it. Atomic theory, guys. Atomic theory. I think we should have started these a little earlier.
Yeah.
All right. Now, basic idea. Again, moving around, playing with gases. He realized that, hey, these have certain properties. Those things he started to describe, through his experiments, to say, hey, you know, all atoms of the same element are the same. All atoms of different elements are different. They're small round spheres, those types of things. I put them in a reaction, hey, it rearranges those same atoms into another structure, giving them different properties. Now, and this is what I kind of just said. Came about in 1808. The date is not necessarily important, but you want to make sure that you know the changes that happened to Dalton's atomic theory. Know what the basic was, but also know the changes that occurred based on research afterwards. Marcus, can you do me a favor? Can you bring me a bottle of water from the back? Compounds are formed, blah, 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 blah. I just said that a second ago, so not going to repeat it. Now, other scientists that sort of came into the mix. We have Gay Lustig, who basically gave us the relationship between temperature and pressure. If you've ever been on YouTube and you watch the video, they lit the candle, they put the egg on top, and hey, it sucked it in. That's basically Gay Lustig's principle. Looking at the fact that as temperature increases, so does pressure. As it decreases, so does pressure. Avogadro, same idea, but he was looking at the volume and the number of moles or molecules inside of a container. If I have two containers at the same temperature, at the same pressure, or not always the same pressure, but same fixed volume, I can determine how many particles are there of both gases. So if I'm looking at, Gay Lustig's results, if I have, I think it's in this one, nope, slightly different. If I have two volumes of hydrogen gas, plus one volume of oxygen, one molecule O2, when they come together, they're going to form two volumes of gaseous water, but the relationship is going to remain very similar. Most people would try to understand this and say, oh, 2 plus 1 equals 3, so this is going to be much larger. No, it goes through a reaction, which is also going to bring down the volume a little bit. So we still are only dealing with volume of the amount of volume for 2 moles of gas. Same ideas, we're looking at hydrochloric acid formation. If I have my 1 molecule of hydrogen, 1 molecule of chlorine, when they come together, those two are going to form 2 volumes of hydrochloric acid or hydrogen chloride if it's not aqueous. Questions, issues, concerns?
Can you go back to the last slide?
The basic idea is we're looking at what's combining, not necessarily how much there is. When we look at the formation of water, most people would think 2 plus 1 is going to equal 3, which is a larger volume. That's not the case because when we bond, the 2 volumes of hydrogen, or the 2 molecules of hydrogen gas with the 1 of water, I get 2 water molecules, not 3. So it's basically just understanding how these things are going to work together. If I have a different structure like we have here, just that 1 single bond, those 2 elements, put 1 of these with 1 of these, I'm going to get 2. Okay?
Can you go back? Yes.
What about it?
That part is not.
All of it's on there.
Well,
I printed it from here.
You can't really see it.
Ah, gotcha. All right. Now, as we move forward, J.J. Thomson, our good friend, brought up the cathode ray tube experiment. Cathode ray tube experiment, he found what again? Electrons. Okay. Now, at the time, what does this fly in the face of? Which principle does this sort of go in? He's the one who developed the plum pudding. We're going back to Dalton, but which of his 5 postulates did we just break? If I have a negatively charged particle inside the atom. Can't be broken nor divided. The atom is what? Sort of. Dalton was saying that it's indivisible, indestructible. Not Dalton. J.J. Thomson comes in, does his experiment with the cathode ray tube. The cathode ray bends away. Sorry. Really? It's not showing it. Bends away from the negatively charged plate, causing them to realize, hey, there's something negative in there. If there's something negative in there, that means that the atom is indeed divisible. Okay? Now, this starts to open the world of atoms because, again, at this point, no one really agrees that the atom actually exists. Can anybody remember who was the scientist who kind of really confirmed that the atom exists? Albert Einstein. Now, let me see, anything, Okay, now, based on this, he determined the charge to mass ratio of the electron, and he figured out that there had to be also positive particles in the atom as well. Now, most people would look at that and say, okay, he found the electron, woohoo! But he went a step further and said there's something positive that we just don't know what it is, or where it is, or how to deal with it. Now, who's the next scientist we should be going to? From J.J. Thomson into who? Millikan is the one that's given on here. He's the one who actually gave us the mass of the electron using the oil drop test. Huh? Henry Becquerel? Now, we usually don't talk much about these two, but it's just basically the idea. Millikan, with his oil drop test, we got the actual mass of an electron. Is that going to help us in terms of what we're doing at this point? No. But what you realize is that is an extremely small value. Because that value is extremely small, if we look at the ratio of the atom mass versus the number of electrons, you'll see that it won't really make a huge effect in terms of the overall mass. Okay? What? I don't know. Now, Henry Becquerel, and we'll talk a little bit about him after the test. They removed a lot of the nuclear stuff, but he discovered radioactivity. He, along with that famous woman, Marie Curie, and her husband. The three of them are the ones who figured out what radiation actually was, emitting energy overall. Now, Ernest Rutherford, the next one that we actually pay attention to. Why? He's the one who gave us the idea that, hey, we have something positive in the center. Now, did he say we have a proton? No. That was James Chadwick a couple years later. But he was the first one to give us the idea that that positive thing that J.J. Thomson was talking about is in the center of the atom. The rest of it is just empty space.
Will this really be on the exam?
They like to ask strange questions. What, especially things around why did the model change? It's not necessarily a thing of just knowing, oh yeah, this was the model. Yeah, who cares? You memorize the models. The question is, how did this model change Dalton's idea? Why did it change Dalton's idea? What's the effect of it changing Dalton's idea?
Did like all these guys work together, or was it all like really separate? Because they all kind of
overlap.
Yeah, almost the same.
One of the last steps of the scientific method that people always forget about is collaboration. Reporting and collaboration. So once they did their results, some of these scientists actually did work together. Some of them, they read the results of someone else's work, looked at it and said, I think I want to try something like this, or I want to try this experiment, and they come out with something new.
Is there like an atomic convention or something?
They actually, if you look up the, the Solvay conference, there were actually large conferences, not like Comic-Con, but sort of similar, where physicists, chemists, all these people would meet together and discuss research and those types of things. We still have it today, but it's not the same thing. More detailed. But yeah. Huh?
So not as large, just the same amount of nerds.
Oh, now it's larger. Now it's larger. Nerds rule the world. It's okay. Now, based on where we got, or where we ended after James Chadwick, we had these three things in mind in terms of our atomic structure. Protons, neutrons in the nucleus, protons positive, neutrons no charge at all. Neutrons also helping with the stability of the nucleus. If we tried to put all the protons together, what would happen? If we just tried to put all protons together, they fly apart. So we have what's called strong nuclear force, which is helping these two to work it out so they stay together. If I get too many neutrons, they spread apart. And guess what? I also get breakdown. That's where we get radioactive decay. Yes?
I know they push each other apart because they have the same charge, but why is that?
What do you mean?
Like why?
Electromagnetic force. That's one of the fundamental forces, electromagnetic force. The fact that they have those same, it's almost like having the same arrangement. If you think about it this way, if you find a person who is too much like you, they'll annoy the crap out of you. That's why usually your best friends are the people who you have some things in common with, but there's enough different where it's okay. Same thing, yeah. As far as explaining why electromagnetic force occurs, that's a physics question. Yeah, but it's more of a just understanding. We know that light repels light. They're going to try to get as far away from each other as possible. The neutrons in there help to balance out so that they're spread apart enough where they don't go crazy. Yes?
Neutrons like spread away from each other too?
Neutrons have no charge.
Yeah, that's why I was confused when you said gravity.
Protons. The neutrons help to buffer.
Neutrons just kind of sit with, they'll just sit with each other.
Yeah, they're the peacekeepers. Now, electrons on the outside, negatively charged. This transitions us into whose model? Who's the first person to organize our ideas about the electron? That one dude. That's it. Niels Bohr. Okay. Now, we talked about this small compared to overall size, the nucleus, and it's extremely dense. Now, at this point, after Rutherford, this is our view of the nucleus, sorry, the atom overall, okay? Now, notice that we're at 2 times 10 to the negative 8 centimeters. Extremely, extremely small, very, very difficult for us to measure. Even most of our measurements are really just estimates. Why?
Because we can't see it.
We can't see it. We don't have anything that really can measure it. So, we get as close as we can. Now,
So will it ever be able to be accurate like that?
we keep getting closer and closer. Closer and closer. Now, another thing that's going to fly in the face of our good friend Dalton, the idea of isotopes. What is an isotope?
Like an element where like it has more or less electrons than it would naturally have.
Ouch. More or less neutrons, yes. Now, this flies in the face of Dalton's atomic theory because, again, he said all atoms are the same element, exactly the same. And then they started doing some experiments and realizing, yeah, that's not it, okay? Now, with our isotopes, same number of protons, different number of neutrons. I think that's kind of funny that you answered that with the answer right there. We ain't going to talk about that. Now, when we look at them, they will have similar properties. So it's not like, oh, we've changed everything completely. We just changed the size of the nucleus, which changes the mass. Most times when we look at that periodic table, it has to represent however many different isotopes that are stable isotopes that there are for that particular element. In the example, if we're looking at 2 isotopes of sodium, both of them are going to have the same number of protons. I don't know how many times in regular honors or AP Chem I've had people tell me that the number of protons changes. Please don't ever say that. You make me want to go and jump out a window. Okay? Only thing that changes, again, for an element, the only thing that makes it that element is the number of protons. So the only thing that can change, we can change the neutrons, we can change the electrons, and it will still be sodium. If we change the protons, we change the element. If I add 1, I get magnesium. If I take 1 away, I get neon. That's it. Okay? Now, when you write the isotopic symbols, there's some you may want to highlight. If it's too small, rewrite. You're usually going to see a symbol that looks like this. It's the element symbol. The mass number is the top number, and the atomic number is the bottom number. So you don't get confused. Yes, that is different than what's on the periodic table. This is representing a specific isotope, a specific atom. What's on the periodic table has to represent all isotopes. That's the one way to remember. It's different. Yes? See a couple pencils still moving, so I'll give you a couple more seconds.
Can I take a picture?
Sure.
Oh, sis.
All right. Changing in 5, 4, 3, 2, moving on. Now, as we look at the structure of the atom, so we're transitioning, as you see, through. We've identified this whole thing with isotopes. The biggest thing that you'll need to know about isotopes, and I think it'll come back later, you'll need to figure out the percent abundance, which is how much of it is usually found in nature, and the atomic mass, and use the formula over and over to convert between the two. I will show you that one. It is not anything difficult. It breaks down to algebra. Okay? Algebra shouldn't be a problem for us, right? Shouldn't be. Okay. Now, moving into the next thing. We talked about waves. Why in the world did we talk about light again? What was the whole point?
Because light is important.
Thank you, Nathan. Light is important. Why? What do we use light to figure out? So we can see what? Not that we can see, but what can we see? So we played around with light, different wavelengths, different frequencies, so that we can figure out what the structure of the atom was. Again, as technology increases, because we learn how to use the stuff we already had. So, the big three that we had to deal with. This one's given to you in your review packet. They tell you what those things are, but you have to be able to use them. Wavelength. What is the relationship between wavelength and energy?
Inverse.
Inverse. What does that mean? Okay. So, which is our highest level energy wavelength?
Gamma rays.
Gamma. Good. Always remember gamma. Gamma's at the end. When you get old, you can become a gamma.
Because
You could. Grandma. Gamma. All right. Now, also remember, gamma waves are short. Grandmas, as they get older, they get shorter. So,
Unless you're and then you start out short.
all right. So, just remembering or briefly covering what we've already talked about. If we look at the different wavelengths, the more cycles, usually going to be the higher the energy. We just talked about this. It just has the scale going the opposite direction. Now, when we look at energy based on light, we're looking at multiples of h nu. When I multiply h and nu, what do I get every single time? What should it multiply and come up to?
energy.
Nathan, do me a favor.
No, I can remember the formula.
Every time I multiply these two values, every single time, it should come back to speed of light. Okay? Every single time. So, that means if I have the speed of light, and I have Planck's constant, which is another one you're given, but you need to remember. For those who sort of, it's given to you in there. I don't know. Equals h nu. There's another one that comes up a little bit later. All right. Now, when it comes to what we did today, how many of you were fine with the open book, open note partner test? Okay. Now, what most people usually think when they hear open book, open note, oh, this is going to be great. I have this person, I have a note, I have this. But if you have not, if you don't know where certain material is in the book, in your notes, or you're working with somebody who has that same mentality or that same situation, it makes things bad quickly. So, that being the case, if ever, because I usually do a take-home test when it comes to acid-base. I might just do an in-class open note partner type of test, and it is an actual test. You want to make sure that you're preparing so that any test you come to, you know where the material is, so you're not searching and taking so much time. Also, by knowing that sort of relationship and where things are, how to find them, how to calculate those type of ideas, it's going to save you time so you can get more done. Now, yes. Huh? Planck's constant.
And the speed of light is always the same.
It's constant as well, yes.
So B is wrong.
Oh, wrong one. No? Okay. Yes, B is the only thing that's changing in that situation. All right. Quanta. So, when we're starting to look at the structure, here's a packet. Here you go. Somebody left the page. There you go. All right. When we look at these little energy packets, we call them quanta, or what's the other thing that we call them? Starts with a P. Photons. Good. Now, how did we use those photons to probe the inner workings of the atom? What were we hitting? Huh? No. What were we hitting specifically? What were we knocking off with electrons? All right. Now, question. How did we figure out where the electron came from? Stop. No. What is that thing called? PES. How do we figure out where the electron came from?
Spectrum.
Photoelectron spectroscopy. based on where we got the peak, it told us how far. The higher it was, the closer it was to the nucleus. The higher energy, the closer it was to the nucleus. Yes. And then we had fun where I kept giving you guys, and then you guys were like, I don't know how many peaks are in there. Is 2p or 1p? That type of thing. Okay. Now, we were able to do that because of the fact that light functions in two ways. It functions as a wave and a particle. That's the only reason why we're able to do this. This is based on our good friend Einstein, who really helped us to understand, hey, the atom is a thing. It's not something we made up and people have been running with for the last couple of years in the photoelectric effect. Now, this is one formula that we can use to calculate the energy of a photon. Equals h nu, which is also hc over lambda, where of course h is Planck's constant, which is given to you here. C is the speed of light, and what is lambda?
Wavelength.
Wavelength. This was Einstein. I probably should have took that slide out, but again, saying the same thing I did, dual nature of light. Now, when we look at light through a spectrum, if I had a prism, I shine white light through it, what do I expect to see? All the colors of the rainbow. Wonderful. Now, if we're looking at it for a specific element, should I see still all the colors of the rainbow? Why not?
Because it's one
All right. What they found is this. With white light, it contains all of the wavelengths that are possible. That's why we get that nice continuous spectrum. When we deal with a line spectrum for a particular element, what we're seeing is the energy drop between energy levels. So this is where we start to get into Bohr, as Kiara brought up, okay? Now, only certain energy levels, this is how we figured out that they were quantized, energy levels are quantized. Once we shine the light through hydrogen, and we get these different bands at different points, different distances apart, we started to realize, hey, I can't have an electron that's hanging out between levels. It's either here or it's here. That's it. Okay? Now, if I hit it with enough energy, I can send it all the way up to the top. What is it called when that electron is not at its ground state? She looks like she's at that state now. The excited state. The excited state. Now, one of the things that they like to do, they'll show you a nice graph with an off-bar diagram with the arrows representing the electrons. And they'll say which one represents an excited state. If it's an excited state, that means you're going to have at least one electron that's not where it's supposed to be. It's going to break the off-bar rule. Nathan, do me a favor, turn around. So you may have one that's up a level or up 2 levels. Okay? Now, what's going to happen as that electron falls down?
It's going back to ground state.
Going back to ground state, but what happens?
More negative.
Hold on. Let's get a full response. You look like you're about to. It releases that energy that it absorbs. Remember, energy is constant. We just talked about that big idea 5, okay? So, the fact that energy goes in, it doesn't stay there. Eventually, it's going to come back down. What pulls it back down to the center?
Gravity.
No. Nuclear charge. Okay? So, we're still looking at this whole big idea. We're looking at a lot of how the nucleus affects the arrangement and placement of the electrons. We just talked about this. N equals 1 is the lowest or ground state. This is showing us where we're at if we're going from 5 to 2 and so forth. They have 3 different series, the Balmer, the something, and the Lyman, something like that. Either way, no, the further it drops, the more energy released. Some of that energy is going to be in the ultraviolet, as well as if it's a very, very small amount, it might be in the radio? Not radio, microwave range. Yes? Like that? Or are you saying for more?
For the actual, like,
The arrow?
yeah, the arrow. Like, are you going to show us what the arrow is?
It could be diagrammed like this. It also could be diagrammed like this.
But it's not going to be like the arrow.
It may not be. Yeah. They like to, as you'll see, and as you saw in your first mock exam, diagrams are big. The fact that you can interpret data in front of you, that is important, okay? 9 times out of 10, the biggest part of chemistry is looking at information, making decisions based on it. So, that being the case, having a line spectra that looks like this, that's open game, okay? Especially these that are down here. Notice that these are all black, but we have blue, green, red. All that's showing is these might be higher in energy, so these might be your UV waves. You're not going to see it part of your light. Not excited, no. I have at least one question that I can pull up for you where we can look at that. All right. Now, this formula you don't need to know, but again, understanding how far it drops determines how much energy is released. This was Bohr's equation, I guess we'll call it, the change in energy, in final, which is the level it stopped at, and in initial, how far it was from the nucleus.
Would they ever ask us to put elements of Bohr's model on the test?
No. No. It's more about, again, it's more about interpreting the model than specific, here's the example.
Will they give us that equation, or do we have to memorize
This, they won't give you this equation.
They won't.
Again, we did this so you'd see the relationship, more so than anything.
it? Will we ever have to calculate that?
Probably not on the test. No. Now, huh? You just boxed it? It's okay. It's one of those things where, what was it? Remember we were talking about electrochemistry, and I said Nernst's equation will not be tested on the exam. Was the E cell equals E standard cell minus? They're not going to test and say use Nernst's equation to solve. But understanding how Nernst's equation works will help you to solve questions. Okay? So if you understand the relationship and what's going to change and how it affects your overall output, that's going to help you. Knowing and memorizing the formula, it's just computation. If you don't know what it means, it's worthless. All right. Now, Bohr's model Bohr is actually feeling pretty good. His model is hanging in there for a couple of years. People are like, yes, you're the man. And then they found out that his model is incorrect because it only works for hydrogen. Huh? Once you add in, imagine this. If I have one electron, right? I can easily track which level it went up to and which level it came down to. Now try to do that with 2 electrons. So this one's going up and this one's coming down. And this one dropped 1 level, this one dropped 3. How can I tell which one released the energy and the distance between? So that type of idea. So once we got past that, Bohr was now feeling a little deflated. It's okay though. He's still a good guy. Now, we move from him into everyone's favorite one to say, Erwin Schrödinger. Or as Todd says, Schrödinger. Yeah. He's in 5th period. Now, very. Now, as we started, hold on, folks. Back to this. All right. Now, as we started to study this, there came a good guy named Werner Heisenberg. Not Breaking Bad, the actual Heisenberg. Now, Heisenberg, looking at the situation that we're dealing with our atom, he realized something. We can figure out where the electron is. Or we can figure out how fast it's moving.
Can't figure out both.
But we can't figure out both at the same time.
Because you need lines.
Now, if I have an electron, it's moving. I have a photon gun. I'm just that accurate. Boom. Shoot it. As soon as that light hits it, what does it do to the electron? It excites it, it moves it. Bounces off. Does something. At that time, it's already knocked it off of its regular course.
Yeah.
So can I then say, oh, it's there. How fast was it moving? I just excited it. I just made it move faster. So that's not going to help me. So I can figure out one over the other. Do you need to know this formula? No. But the basic idea is we can use this formula if necessary to figure out where it is or how fast it's moving, not both at the same time.
You said it was both.
Not at the same time.
Oh, okay.
Now, Schrodinger comes in and he has his wave function equation. This is where we have these people moving towards math. Bohr was a physicist, Rutherford was a physicist, Schrodinger was a physicist. Okay? Physicist. Now, Schrodinger looking at this very, very complicated equation. If you want to see it, just look it up or I'll find it for you. Figured out that around the atom, we have this probability distribution. We have points where we may be able to find an electron. Higher probability, of course, is going to be closer to the nucleus. As we get further and further away, that probability drops significantly. And that's what we're seeing here. Notice we never drop to zero. We just get really, really close. Okay? Now, this is looking at a 1s orbital. So we know we're looking at something that's very, very close to the nucleus as is. Yes, whoever sneezed, you heard the person say it. Now, as we look at it, again, right next to the nucleus, we get a peak just a little bit further, and then we get out. Again, it diminishes as we exit the nucleus. Now, because of this fact, we cannot say this orbital is exactly this size. We love to be able to, but we can only make predictions based on what we have. So, when we look at electron density, looked at the orbital, we say it has a 90% probability that it's going to be close to the nucleus. 90% is pretty high. Yes?
Is it that we don't have the information or the technology to know how big normal is, or it's just impossible?
I'm going to show you in a second. We have some technology that will give us an idea. But again, we have an electron that's moving around in all different directions at the same time. So you can't say, oh, it has this path, so let me go ahead and just see exactly. It's moving this way and then it's moving that way because it's also repelling against other electrons that are there. Okay? Now, in order to start understanding this, we came up with this whole thing of quantum numbers. Who has time? What time we got? 3:15? Okay, so we got about 15 minutes. All right, we came up with this whole thing of quantum numbers. Now, quantum numbers are sort of like the electron's address. Figure out, first off, what energy level. How do we know which energy level based on looking at our periodic table? Not the periods. Okay. So, moving down. The next thing we look at is the shape of the orbital, which is given to us by L. And that's where we get to our subshell, our SPDF. Next, we get to a magnetic quantum number, which again is telling us how it's oriented in space, whether it's along the X, the Y, or the Z axis. And then we also have what's called the quantum spin. Now, over time, they realize that this is nice, but it's not as necessary as we would love it to be. And so, we're able to take information from this and start to come up with some other designations that we can utilize instead. Instead of having to go through and write, and we literally had to write pages and pages, depending on which element, because it's for every single electron. Instead of having to do that, we use the electron configuration. Now, this is those same probability distributions. The further we go away, the more interference we get between the electrons, which are also moving as waves and particles. When they collide, they hit points. We get these things called nodes. So it's almost like a little point where everything dips down. It's the interference of one wave that's up, one wave that's down. Now, Nathan, this goes back to your question. What we're looking at is, this is one of those plots of the electrons, okay? And they found, if I'm looking at a p orbital, it has about, or the bulk of the time, that 90% area where they hang out looks like this. Now, will I find some electrons outside of that area? Definitely. But the highest probability is going to be within this certain space around the nucleus, which is here in the center. Notice we have that blank spot. Okay? Huh? When they came up with these shapes, it's based on the fact that this is where we find the electrons 90% of the time. This is what it looks like from what we plotted. Now, this is also where we get some of those very, very strange.
Sorry, can we go through that whole way real quick?
All right. This is where also we get a lot of those strange shapes. No, they were not just bored and made up some shapes and said, ha, this is what we'll use from now on. They actually had data. Notice in the center of every single one, why do we have a blank spot here? Because that's where the nucleus is. Great. And again, the further we get away, the shapes get weirder. But overall, the highest energy levels are the ones requiring the highest amount of energy, being our f orbitals, lowest amount of energy being our s orbital. How many s orbitals does each energy level have? How many s orbitals does each energy level have? How many p orbitals does each energy level have? How many d orbitals? And f orbitals? Wonderful. How many p orbitals does the first energy level have?
6.
How many p orbitals does the first energy level have? 0. I heard somebody say 3 and it scared me. First energy level only has which orbital? S. Stop pointing at people. When we look at our first energy level, the most it can hold is 2 electrons. We talked about that. S orbital can only hold 2. That's our hydrogen and our helium. After that, that orbital is filled. We'll move on to the next one. Spin. We'll come back to that at another point again. Quantum numbers, you don't need to know as much. Just understand every electron has an address. We're going to pass through some stuff. All right. Now, moving back into our periodic table. We get to our good friend off-ball. Off-ball, electrons are lazy. That's how I always remember it. Electrons are lazy. They always start with the lowest energy level and move up and fill. This is how you can tell whether you have an electron in its excited state. If everything has been filled up to here and then randomly I get an empty space with an electron hanging out up here, I violated the off-ball principle. Most likely that's at an excited state. Okay? And that's explaining the same idea. I had to go through the 1s, 2s to get to the 2p to fill. Hund's rule, I think, seat on the bus theory. Everybody wants their own seat, if possible. And then, if they have to share it, they will. Same thing with our electrons. Okay? If I have a p orbital set in my second energy level, I have 3 spaces where electrons can hang out. They're not going to go and double up right away. That causes strain because, again, those electrons want to get as far away from each other as possible. So, to stabilize the atom, we get 1 in each of those orbitals, subshells, and then it goes back to double up. Now, this is also the reason, I believe we talked about this several times, why oxygen has a lower ionization energy than nitrogen. Does anybody remember?
You want to say it again?
Why oxygen has a lower ionization energy than nitrogen.
Because there's more electrons. And they want to so that's easy to take one.
It has to do with the 2p subshell, but what was it that's happening in that subshell? You said the exact correct answer, but you said it so quietly. Can you say it a little bit louder for me?
What?
Okay. Because when you look at it, and I wish I would have had this up here, I'll draw it out at another point. When we look at our nitrogen versus oxygen, in our 2p orbital, nitrogen has 3. We have 3 spaces. Each of those electrons are spread out. They're more stable, we'll say. They're more stable than they would be. Oxygen has that 4th electron. So one of those orbital spaces, I have to double up. That's creating strain. That's why we get that little bit of a dip. Remember, when it comes to ionization energy and those types of things, they do like to ask about why is there a difference? Why does this one not follow the trend? And it usually goes back to structure. Questions, issues, concerns? Yes, sir.
So then, does fluorine have a higher or lower ionization energy than oxygen too?
No, higher.
Higher?
But why?
Because then there's more orbitals filled, I guess.
More orbitals filled, what is it closer to?
Double gas.
Noble gas configuration. So once it gains that extra electron, it releases a bunch of energy. It has a high electron affinity, releases a bunch of energy, and becomes very, very stable. Fluorine, when we start talking about acids and bases, a lot of people make the mistake of thinking hydrofluoric acid is a weak acid, so that means it won't do anything. That's the one that will eat through just about anything except certain types of plastics. Now, orbital diagram, this is what I was talking about before. Everything fills accordingly. I think I might have had, no, I did not have one. Yeah, give me the example. Where we at on time? 7 minutes left? All right. Now, when we start talking about, and notice I've run through this pretty quickly, so I know some of you are probably like, okay, got a lot of stuff to do.
Yep.
That's perfectly fine. Mondays and Fridays, I still will be here for tutoring, but yeah, make sure you come with questions, not teach me. All right, now, when we talk about valence electrons, we know these are the ones that are going to be in the outer shell. These are usually going to come from which two orbitals? They'll only be of these two orbitals.
Wait, say that question.
S and P. Our valence electrons will always be from our S or our P orbitals. That includes if we're dealing with transition metals. Okay? Most people make the mistake and say, oh, well, the transition metal has to come from the D orbital. No. It's still coming from the S orbital when it loses. Okay? Now, why? Because those are the ones that are going to be protruding out the most. It's going to be the furthest out, easiest to access. When we look at filling, and yeah, I told you guys the way to do it. Reading your periodic table is just like figuring out the orbitals. Each energy level is a period, and then your blocks, S, D, P, F. Some dogs play fetch. The easiest way to remember it. Yes.
Okay. When you're at 6S,
Yes.
and then you're going on. Okay, are you supposed to go straight down there, or should you count LA as 5?
When you leave 6S, this is just saying lanthanides. That's why LA is there. But you're going to go down to 4F, which will then bring you back up to 5D, and you'll continue from
Then
there.
I'll start after I come up from F, and I'll go back up to
5D, 6P, 7S, 5F, so
I
forth.
mean, like,
Whoa, what?
right after I get off of RF, like when I finish the last one, do I go to LA or do I go to the second one? LA?
What?
Yes.
Wait,
Make sure.
Yeah.
He just
Yeah, all he was asking is, do I have, what is it, Lawrencium? Lanthanum, sorry. Lanthanum. After I finish this, would I have left lanthanum before, or